Inferential statistics. Population and sample proportions, margin of error and confidence intervals. Suppose there are two candidates in a presidential election, A and B, and that we want to estimate as a percentage, for example 45%, or as a decimal, for example 0.45, the level of support for candidate A. This measure is called the proportion of the population that supports candidate A. It is common practice to let the population proportion be denoted by the letter P. Notice that there is no standard deviation, as the proportion is just a single number. Now suppose that we select a simple random sample, an SRS, of 200 voters and ask them which candidate they support for the upcoming election. Let the sample proportion who support candidate A be denoted by P hat. So it's like a P with a little arrowhead on top. So P represents the population proportion, so the full population proportion, and P hat represents the sample proportion, so just the sample of the full population. It is not reasonable to expect P hat to be exactly the same as P, but it is likely to be not too far away, so we expect them to be close enough but not the same. Common sense tells us that increasing the size of the sample we take will increase the probability that P hat is close to P. So how can we quantify our confidence that the proportion we get from our sample is close to the population proportion? So basically, how confident are we? We do so by introducing quantities such as the standard error of the proportion, the margin of error, and confidence intervals. So this video will focus mainly on the margin of error, but in the next video it will focus on confidence intervals. The theory. When we take one sample of a size 200 voters and calculate its proportion, P hat, we are only finding the proportion from one of many samples of size 200. If we were to consider all such proportions, we would have the sampling distribution of the proportion. The sampling distribution of the proportion, i.e., that is, the distribution of all possible sample proportions for samples of the same size, has the following properties. So property 1, it is normally distributed. So we would have a bell-shaped curve. Property 2, its mean, written as mean with P hat stuck onto it, is P, the true proportion of the population. Property 3, its standard deviation depends on the size of the samples. The larger the sample size, the smaller the standard deviation. The standard deviation of the sampling distribution of the proportion is called the standard error, SE, of the proportion, and it's written as the standard deviation symbol with P hat stuck onto it. So this symbol here represents the standard error of the proportion. The formula for the standard error of the proportion is given on page 34 of your formulae and tables, and it's given as the standard error is equal to the square root of P times 1 minus P divided by N, where P is equal to the population proportion and N is the size of the samples. So here we have our sampling distribution of P hat. So it's our normal bell-shaped curve. So it's a symmetrical curve. So our line of symmetry down the centre is P. And remember, P is the population proportion. From the centre over as far as here, we have capital E, which is the margin of error. Therefore, this point here is P plus the margin of error. And likewise on the other side, this point here is P minus the margin of error. So capital E stands for the margin of error. And then from the centre to this point here, so basically this dotted line, is the standard error of proportion. Thus, if we know the true population proportion, P, we can use either the empirical rule or the standard normal tables to estimate the probability that a particular sample proportion will lie within a certain distance of the population proportion. So we want to work out the probability that a certain sample proportion lies within a certain distance of the population proportion. So the empirical rule only gives a rough guide, while the standard normal tables gives a more accurate estimate. The approach used is to form an interval in which we can be C% sure that the true population proportion lies. So, for example, if the true population was 10%, but we did not know that, we might be able to work out that the true population lies between 5% and 15%, for example. So we're trying to come up with an interval in which we know that the true population proportion lies. And we are going to be a certain percentage confident of that. So C% is called a confidence level. And from the point of view of calculations, C is written as a decimal. The most commonly used confidence levels is 95%. So C is equal to 0.95. So for example, I may say that I am 95% confident that the true population proportion lies between 5 and 15%, and so on. But others you may meet are 90%, so C is equal to 0.9, and 99%, so C is equal to 0.99. So for example, I may say I am 99% confident that P, the true population proportion, lies between maybe 20% and 30%. For the confidence level chosen, we can construct the interval in which the probability of a sample proportion lying is C as a decimal. This interval is called a C% confidence interval. So an example is a 95% confidence interval. This interval is centered on P, the population proportion. The distance from P to an edge of the interval is called the margin of error, and it's denoted by a capital E. The margin of error E will depend on C, which is the confidence interval, P, which is the population proportion, and N, which is the size of the sample. And we'll see how to calculate it below. Once E has been calculated, the confidence interval is then P minus E, comma P plus E. So P being the population proportion, minus E, the margin of error, comma, P, again the population proportion, plus E, the margin of error. So this will give us our confidence interval. So for example, we may say we are 95% confident that P lies between this and this. The practice. This is fine in theory, but in most cases we do not know the true population proportion. This is what we are trying to estimate. So we turn the argument on its head. Just as we can say that there is a probability of C that a sample proportion P hat lies in the interval P minus E, comma P plus E, where the P's stand for the population proportion and the E's stand for the margin of error. We can also say that there is a probability of C that P, the population proportion, lies in the interval P hat minus E, comma P hat plus E. So again, where E is the margin of error. So our curve looks very like the one we saw previously, except our line of symmetry, we no longer have P, we now have P hat. Again, from the center to this point here, we have E, the margin of error. So this point here is P hat plus the margin of error. And this point here is P hat minus the margin of error. And from here to here is still the standard error of proportion. The problem is that because we do not know the value of p, we have to use p hat instead of p if we need to calculate the standard error of the proportion. Thus we use, so we're going to use this formula, and it's the exact same as our previous formula, except we're swapping p for p hat. So we have the standard error of the proportion is equal to the square root of p hat times 1 minus p hat divided by n. So this is for the standard error of the proportion. So this is where p hat is the sample proportion and n is the size of the sample. Margin of error approximation for 95% confidence interval. The empirical rule, which states that approximately 95% of the area, or probability, under a normal curve lies within 2 standard deviations of the mean, can be used to obtain a rough approximation. So E, the margin of error, is equal to twice the standard error of the proportion. So we can see down here E is the margin of error, and our standard deviation symbol with p hat stuck on is our standard error of the proportion. And since the standard error of the proportion is equal to this formula, as we saw on the previous slide, then this is equal to this, or p hat instead if p is unknown. To be as safe as possible, we want to allow for the largest possible value of this expression. By calculus, or by completing the square, we can find the maximum possible value for p times 1 minus p occurs when p is equal to a half. So when p is equal to a half, we get p times 1 minus p, which gives us a half times a half, which is a quarter. Thus, E, the margin of error, is equal to twice the square root of 1 over 4n, which is equal to twice 2 times 1 over 2 root n, and the 2's will cancel, leaving us with 1 over root n. So basically this is our formula for the margin of error. And this is a very rough approximation to the margin of error at a 95% confidence level. So this can only be used for 95% confidence level. So approximate margin of error at the 95% confidence level. Suppose a sample size of n gives a proportion p hat for a certain characteristic. Then we can be 95% confident that the proportion for the whole population p lies within the margin of error of p hat. So the margin of error is given approximately by E equals 1 over root n. So E being the margin of error. Thus, the 95% confidence interval for P is P, which is the population proportion, is greater than P hat minus 1 over root n, and is less than P hat plus 1 over root n. So P hat being the sample proportion and P being the population proportion. So it's basically the sample proportion minus the margin of error, which is E, and the sample proportion plus the margin of error. A survey is conducted to see what proportion of soup buyers chose brand A of soup over all other brands. A random sample of 600 shoppers who buy soup is taken and returns a proportion of 33% who chose brand A. So there was a sample of 600 shoppers, and it turned out that a proportion of 33% of them chose brand A. Part 1, we want to calculate the margin of error at the 95% level of confidence. So we will use the approximate formula that E equals 1 over root n, unless we're asked to be more accurate. So if they asked you to be more accurate, or they asked you to use the standard tables, then you would do so, but otherwise it's okay to use this. So E, the margin of error, is equal to 1 over root n, and n is 600 because that's what the sample was, so 1 over root 600 is 0.0408. So this is the margin of error. Part 2. Give the 95% confidence interval for the true proportion of soup buyers who chose brand A. The 95% confidence interval for P, the true proportion of soup buyers who chose brand A, is P greater than P hat minus 1 over root n, and P less than P hat plus 1 over root n. So P hat is 0.33 that was given in the question. That was the sample proportion. 1 over root n we worked out to be 0.0408, and subtracting we get 0.2892. And then adding we get 0.3708. So P, which is the true proportion, the true population proportion, lies between 0.2892 and 0.3708. So our sample proportion, it worked out to be 33% chose brand A, but of the actual population, the true population proportion, we are 95% confident that it is not 33%, it's somewhere in between about 28.9% and 37.1%. Part 3. With 95% confidence, what is the highest proportion of soup buyers who could choose brand A? So with 95% confidence, the highest proportion who could choose brand A is 33% plus 4.08%, which is 37.08%, which is basically this decimal. Here is a percentage. So this is the highest proportion who could have chose brand A. And likewise, the least proportion, or the lowest proportion who could have chose brand A would be 28.92%. Part 4. How could the margin of error have been reduced? And are there any implications of taking this action? So remember, our margin of error was 0.0408, or you could say 4.08%. So how could this number have been made smaller? How could our margin of error have been reduced? The margin of error could have been reduced by increasing the sample size. So increasing the 600 to a much bigger number. That would reduce the margin of error. Increasing the sample size incurs extra costs, which might be considered disproportionate to the reduction in the margin of error. A political party supports candidate A in an election with 2 candidates. Earlier polls indicate that voters are very evenly split between the 2 candidates. The political party wishes to conduct a random sample of voters to determine the level of support for their candidate to within 1%. Money is no object. What sample size, so what N, should they take at a 95% confidence level? So, to within 1% means that the margin of error should be 1%. So we're going to let N be the size of the sample to be taken. So remember, that's what we're looking for. We're looking for the sample size. The margin of error is 1%, which is the same thing as 0.01. So what we're going to do is let the margin of error formula, which is 1 over root n, equal to the actual margin of error, which is 0.01. And then we just solve for n. So we have 1 over root n is equal to 0.01. So multiplying both sides by root n, we get 1 equal to 0.01 root n. And then dividing both sides by 0.01, we get the root n on its own. So we have root n equals 1 over 0.01. And 1 divided by 0.01 is 100. And squaring 100, we get 10,000. So n is equal to 10,000. So a sample size of 10,000 would be required to obtain a margin of error of 1%. So I could only use the 1 over root n formula for the margin of error because the question specifically said it was a 95% confidence level. So if this question had instead asked us to be within 2%, then we would have let 1 over root n equal to 0.02 and solved for n. If it had said to within 5%, we would have let 1 over root n equal to 0.05 and solved for n, and so on.